The gate is connected to ground, and there is a load resistance here, RL. I will consider an input current II in parallel with a resistance RS, and this is GM VGS, where VGS is this voltage. This is the gate, this is the drain, and this is the source. Okay. Now we can do the analysis properly. If we take VGS as this variable, this is at 0 volts, so the voltage at the source terminal is minus VGS. Okay, and the current flowing in RS is upwards, and it's equal to VGS by RS. Okay, and the sum of these two, GM times VGS and VGS by RS, equals II. Okay, so II equals GM times VGS plus VGS by RS. Okay, or this can also be written as VGS times GS, where GS is the conductance of the input current source. Okay, so VGS will come out to be II divided by GM plus GS, and the output current I naught, what is that? That is GM times VGS. So I naught is GM divided by GM plus GS times II, the input current. Okay, what did we want? We wanted I naught to be equal to II, and you can see that this reduces to that. It's approximately equal to II if GM is much greater than GS, or put another way, GM RS is much greater than 1. In fact, we have been seeing similar expressions everywhere, in case of the source follower, in case of the voltage controlled current source, and here as well. This GM times whatever resistance is connected between its source and ground. It happens to be the load resistance in case of a source follower. It happens to be the resistance which defines the transconductance in case of a voltage controlled current source, and here it's the internal resistance of the input source. That must be much greater than 1. In that case, this behaves like a current buffer of gain 1. Okay, so this is a pretty simple linear circuit. I am assuming you can analyze that. If you didn't get this answer, please go back and analyze this. This is extremely simple. You will find that I naught is GM by GM plus GS times II, and it's very close to II if GM is much more than GS. Okay, now what about the input and output resistances? The input source is connected between this point and ground. Okay, so that's where we connect the input source, and I will evaluate the input resistance by applying a voltage V test and measuring the current I test. This is very easy. The gate voltage is at 0, the source voltage is at V test. So the gate source voltage VGS is minus V test. Okay, so this current downwards is minus GM V test, or upwards it is GM times V test. So the input resistance Ri, which is V test by I test, this equals 1 by GM. Okay, so the input resistance of this is 1 by GM. Notice that in both the calculation of the gain I naught by II and in the calculation of the input resistance, I have neglected RDS, because including RDS it will change the expression, but assuming that RDS is quite large, it doesn't make any qualitative changes, so I've ignored that. The last thing we have to evaluate is the output resistance. The output resistance, of course, we have to include the input source II, which is set to 0 in parallel with the source resistance RS. Okay, and this is GM VGS, this is VGS. Okay, and the load is connected between this point and ground, and that's where we have to evaluate the output resistance. Now in this case, when you set II equal to 0, and if this is all the circuit, you see that the consistent solution is for this voltage to be 0 and this current source to be 0 and consequently an open circuit. Remember, this is exactly the same thing that we evaluated for the output resistance of a voltage controlled current source. It's exactly the same thing. We had called this R1 there, now we call it RS. Okay. So if you evaluate R out with GDS equal to 0 or RDS equal to infinity, it will come out to be infinity. It will appear like an ideal current source. So in this case also, the presence of RDS makes a qualitative difference. Okay, it will make the output resistance to be different from infinity. It will be finite, and I won't evaluate this again. As I mentioned earlier, in case of the voltage controlled current source, it's easiest to evaluate it with a current input I test. Then you can first calculate this voltage and then calculate VGS from there, calculate the current flowing through RDS and find the answer. The answer turns out to be R out will be GM times RS times RDS plus RDS plus RS. Okay. So although it's not infinite, it is much greater than RS. What is RS? It's the resistance of the input current source. The resistance of this current controlled current source is much higher than that. The output resistance is much higher than that. So what it means is, it gives you the same current value because the current gain is 1, but with a much higher output resistance, meaning it becomes a much better current source. Okay. And of course, R out is also much greater than RDS, which is just the output resistance of a transistor, because for this current buffer to work properly, you have to choose GMRS to be much more than 1. Now there are these other terms also in the output resistance, and they will be much smaller than this term, which will be the dominant one. Okay. So in summary, our current controlled current source, the small signal picture looks like this. The gate is connected to ground, and the input source is connected to the source terminal. This is II and RS. This is VGS and this is GM VGS. This is RDS and we have RL. This is the output current. What we have calculated so far is that I0 by II equals GM by GM plus GS approximately equal to 1 if GM is much greater than GS, and the input resistance Ri is equal to 1 by GM. Okay. Now both of these expressions have been evaluated with RDS equal to infinity or GDS equal to 0. I would encourage you to try it out with RDS not being infinity. You will get a more complicated expression, of course, but essentially the result will be these two. Okay. Now as far as R out is concerned, it doesn't make sense to neglect RDS, because in that case we simply get infinity as the answer. R out will be GM RS RDS plus RS plus RDS. Okay. So it does behave like a current buffer. It has a small input resistance. Okay. What does small mean? It is small compared to the resistance of any current source that you connect. It should be small compared to RS, and it will be the case because GM has to be much greater than GS, and if you rewrite it, RS will be much greater than 1 by GM. Okay, the input resistance of the current controlled current source will be much smaller than RS. That has to be the case. And then R out will be much more than RS. So it takes a bad current source and gives you a much better current source. That's the role of a current buffer. Okay. This is the current controlled current source with a gain of 1, and you can see in this case that this is the gate, drain and source terminal of the MOS transistor. The input is applied between source and ground, the output is taken between drain and ground, and the gate is grounded. So we can say that the input is applied between source and gate, and the output is taken between drain and gate. Okay, and because gate is common to the input and output, this is also known as a common gate amplifier. Okay, so it's a current buffer or a current controlled current source of gain 1, and it's also known as the common gate amplifier. It's one of the basic building blocks using a single transistor. Okay.